Yeah, my name is Nael Alsaleh. I'm currently a postdoctoral researcher, and I'm working with Professor Eric Miller on the operation and planning of autonomous vehicles. And before that, I graduated in December 2022 from Toronto Metropolitan University. And today, actually, I'm presenting one of the projects that I worked on during my Ph.D. on the sustainability analysis of on-demand public transit. So the presentation actually is divided into 5 main parts. I'll start with a brief introduction and the main motivation of the work. Then I will discuss the proposed framework for assessing the sustainability of on-demand public transit, and then the application of this framework on a case study, results, and I will conclude with a few remarks and key takeaways. So fixed route transit system offer a set of well-defined stops and times to serve passengers along a predefined route. However, the system is not always efficient or cost-effective, especially in low-density areas. Actually, transit operators in such settings tend to reduce the frequency, operating hours, and adjust the spatial coverage in order to increase the occupancy of vehicles and reduce their operating costs. And these circumstances can adversely affect the performance of the public transit system, leading to a greater reliance on private vehicles. However, with the advancements in the information and communication, several on-demand transit systems have emerged as innovative solutions in low-density areas. And in this work, we classify on-demand transit systems according to their supply resources into first, dedicated fleet on-demand transit services, where the fare is primarily fixed, fleet size remains stable, vehicles are often owned by organizations, and drivers receive fixed salary. And second, we have crowdsourced on-demand transit, which represent subsidized ride-sourcing services. And in this system, the fleet size is flexible, vehicles are privately owned, and drivers have variable income. And the third system we have is the hybrid system, where both crowdsourced and dedicated fleet coexist. In terms of the vehicle size and the level of sharing, actually the dedicated fleet on-demand transit operate with higher capacity vehicles and provide higher level of sharing. So by adapting to users' schedules and routes, on-demand transit systems can provide better service quality than fixed route transits in low to medium demand areas. And they offer transit operators a new opportunity to deliver convenient, attractive, cost-effective, and sustainable transit systems, and theoretically can contribute to social equity and inclusion by facilitating mobility or travel for disadvantaged communities and improving mobility for everyone. However, the efficiency of an on-demand transit system is highly dependent on the number of ride requests the system receives and their distribution over space and time. And the realization of the desired benefits actually depend on the suitability of the implemented system, as well as the effective design or its effective design and operation. And in fact, there have been several instances where the adoption of on-demand transit system hasn't been suitable or cost efficient, and the system has to be suspended. And it's worth noting that on-demand transit services are still in their early days, with only a limited number of projects being in place. With this in mind, it's very important, and there is a strong need to understand where and when each type is most efficient and sustainable. Therefore, this work actually aims to provide a comprehensive framework for assessing the sustainability of on-demand transit systems. And the framework is used first to evaluate the overall efficiency, environmental footprint, as well as social equity and inclusion, and after that, identify the demand switching point between different on-demand transit configurations. And this brings us to the framework. So, simulation tools can be used to compare and evaluate different on-demand transit services within study area and without incurring the full implementation cost and risks. And the main impulse to model on-demand transit systems include the transportation network data, network traffic demand, public transit usage data, and the operational characteristics of on-demand transits. Then, several simulation scenarios can be developed by changing these characteristics. And the main factors that affect the performance of on-demand transit systems include the coverage area, supply settings, and demand-supply interactions. Also, the type of service is another influential factor for the crowdsourced on-demand transit, where we have either exclusive rides or shared rides. After that, the simulated transit systems can be evaluated using a range of indicators, which can be classified into user performance indicators and indicators related to system efficiency. And the user performance indicators include worker time, waiting time, in-vehicle travel time, and trip length, while indicators of system efficiency include the cost, unmet demand, GHG emissions, and vehicle kilometer traveled per mile. These indicators are then used to evaluate the sustainability in terms of overall efficiency, environmental footprint, and lastly, the social equity and inclusion. To compare the overall efficiency of different public transit systems, prior literature have used different approaches, like the total travel time, or the weighted sum of walking time, waiting time, and in-vehicle travel time, or the generalized cost approach. And in this framework, we adopt the generalized cost approach because it provides a more holistic approach, like by combining and using or taking into account both the user performance and the operator costs. It simply determines the overall efficiency of an on-demand transit system by combining its net annual cost with the equivalent monetary value of users' total waiting time. And to convert users' total waiting time, total travel time into the equivalent monetary value, we use the value of time. Then, the critical demand densities can be identified by comparing the generalized cost values of different on-demand transit services over a range of demand levels. To assess the environmental footprint, we use 3 different indicators: vehicle kilometer traveled per passenger. We use the total yearly GHG emissions and GHG emissions per passenger kilometer. And lastly, the social equity and inclusion. Here we adopt the Lorentz scale and Gini coefficient to evaluate the social equity and inclusion. And these methods have been widely used in the literature to evaluate the equity of transportation services in general. The Lorentz curve actually illustrates the inequality of a distribution graphically, while the Gini coefficient measures the level of inequality mathematically. And here we are using them to first assess the equity distribution of the public transit use, and then the equity distribution in waiting and in-vehicle travel time for different on-demand transit configurations among disadvantaged groups. The framework is applied to the town of Innisfil, which is located in the northern edge of the Greater Toronto and Hamilton area. Innisfil has a population of 37,000 residents, a land area of 262 square kilometers, population density of 140 residents per square kilometer, and median income of 72,000 Canadian dollars. In May 2017, the town collaborated and partnered with Uber to provide residents with a subsidized crowdsourced on-demand transit service instead of investing in a new fixed-route transit system. And here we develop a micro-simulation model calibrated on actual on-demand transit data from Innisfil. The transportation network was extracted from OpenStreetMap. The Innisfil provided us with the actual operational data for the crowdsourced on-demand transit service, and the average daily demand value was utilized from the 2016 Transportation Demand Survey. In total, 9 different on-demand transit configurations were simulated separately, were developed and simulated separately, and the simulation covered 24-hour period, and in all scenarios, the demand ranged from 50% to 500% of the base demand level, which is 177 passengers per day, representing March 15, 2021 demand data. The first 4 scenarios simulated the existing crowdsourced on-demand transit system in Innisfil with and without ride-sharing. And in both cases, in both cases, 2 scenarios were created. In one scenario, the supply remained constant while increasing or decreasing the demand, while in the other, the supply followed the demand linearly with a slope of 1. So the first case actually represents the worst case scenario where there is a shortage in supply, while the second one represents the best case scenario where there is always sufficient or enough supply. The next 3 scenarios involve modeling a dedicated fleet on-demand transit system, and here we created 3 scenarios for them. The first one with constant supply, the second one, and the other 2 ones actually, they are the supply followed the demand linearly with slopes of 0.5 and 1. And the main philosophy behind that was to find and identify the most cost-effective supply settings, as in this system requires the purchase of public vehicles. Lastly, 2 scenarios were created for hybrid on-demand transit systems. One scenario involved a hybrid system that combines fixed route transit with crowdsourced transit service. And the coverage area and operating hours of the fixed route transit was identified based on an analysis of the actual origin-destination flows of the existing crowdsourced on-demand transit in Innisfil. The other one involved modeling a hybrid on-demand transit that combines dedicated fleet on-demand transit system with crowdsourced on-demand transit system. And the dedicated fleet on-demand transit was designed to cover the same area and operating hours as the fixed route transit in the previous scenario. And these figures actually represents the dispatching algorithm that was used for different systems. So the first one represents the greedy algorithm that was used for the crowdsourced on-demand transit without ride-sharing. And the greedy algorithm is a predefined algorithm in Sumo that assigns vehicles to the nearest waiting passengers based on the first-come, first-go approach. The second one represents the shared greedy algorithm that was used for crowdsourced on-demand transit with ride-sharing, and it's a modified version of greedy algorithm, but it picks up another passenger while heading to the first passenger destination. And the third one represents the demand responsive tool that was used for the dedicated fleet on-demand transit. And in this tool, actually, it aims to maximize the number of served demand while minimizing the number of operating vehicles and satisfying some constraints, such as the maximum waiting time and maximum detour. Okay, so let's move to the results. Actually, the results are presented in the following order. So first, I will discuss the user performance indicators, operator cost, critical demand density, environmental footprint, and lastly, the equity and inclusion. So, user performance indicators. On average, users walk for 6 minutes in the fixed route transit-based hybrid system. And for other transit systems, the walking time is assumed 0 because these services provide door-to-door service. The lowest waiting time, in-vehicle time, and average trip length are observed with the on-demand transit-based hybrid system and crowdsourced on-demand transit with increased supply. On the other hand, the maximum occupancy rate and waiting time are associated with the dedicated fleet on-demand transit with constant supply, when the demand is below 354, and after that it's associated with the crowdsourced on-demand transit with constant supply. And to understand this, actually we need to look at the unmet demand. So here we can see that the dedicated fleet reached its capacity at 354, and the system fails to accommodate most ride requests after this point, resulting in a sharp drop in the average occupancy, in-vehicle travel time, average trip length, as well as the average waiting time. Moving towards the cost. So, crowdsourced on-demand transit systems have no capital cost because it operates privately owned vehicles. On the other hand, you can see that the maximum or the highest capital costs are associated with the dedicated fleet on-demand transit because they use public vehicles and they require to purchase these public vehicles. If we move to the net operating cost and the total annual cost, we can see that the lowest net operating cost and total annual cost are associated with the crowdsourced on-demand transit system with increased supply when the demand is below 266 and 292. And after that, the fixed route transit-based hybrid system becomes is associated with the lowest operating and annual cost. So here we evaluate these indicators independently and separately. But to evaluate the overall efficiency of the system, we use the generalized cost approach one. So in the generalized cost approach, or this figure provides the overall efficiency of the transit systems. And here we can see that the crowdsourced on-demand transit system with increased supply are the most cost-efficient transit system at all demand levels below 3.37. And 3.37 actually represents the 885 passengers per day divided by the area of Innisfil, just to give a sense of the intensity of the demand there. However, both the fixed route transit-based hybrid system and the crowdsourced on-demand transit system with increased supply have approximately the same generalized cost value when the demand is at 3.37. These values, however, do not consider the impact of surge pricing. So we introduce 3 cost increments on the operating cost of crowdsourced on-demand transit system to account and to capture the impact of surge pricing on the critical demand densities. So at 20%, 40%, and 50%. And we can see that the critical density value between fixed route transit system and the crowdsourced on-demand transit systems decreased to 2.12, 1.30, and 1.1, respectively. Then we have the environmental footprint. And here, in comparison to other transit systems, we can see that the dedicated fleet on-demand transit with constant supply has the lowest vehicle kilometer travel per passenger, total yearly GHG emissions, and the GHG emissions per passenger per kilometer. In contrast, crowdsourced on-demand transit systems with, in general, actually have the highest vehicle kilometer travel per passenger, GHG emissions, and GHG emissions per passenger kilometer. But contrary to expectations, transit systems produce more GHG emissions than passengers driving their own vehicles for the same trip at all demand levels, which is the baseline scenario marked here and represented by the orange line. So in other words, the use of private vehicles is more environmentally sustainable at all demand levels than providing public transit system. And there are 2 possible reasons for this actually. First, if we go back to these maps, so transit systems are covering a large area of 262 kilometers, square kilometers, while the demand is not evenly distributed. So vehicles are making long dead-heading trips and large detours in case of shared trips. While in the baseline scenario where they are using their private vehicles, the passengers are heading directly from their origin to their destination. So this is the first reason. And the second one is that we are using larger vehicles for transit systems, 8-seater vehicles. But they may not be large enough to provide the level of sharing that results in lower per passenger kilometer GHG emissions. But in the future, when the town grows and the network becomes more congested, providing higher capacity vehicles can produce lower GHG emissions per passenger kilometer. And these values actually represent the most conservative scenario where all vehicles are gasoline powered. So we considered the assessment of the environmental footprint for the transit systems at 5 different electrification levels, 20% to 100%. And the electrification of the entire fleet would save approximately 98% of the total GHG emissions produced by the transit systems. The last part of the results is related to social inclusion and equity. So here we start by evaluating the social equity and inclusion in the current use of the existing crowdsourced on-demand transit system in Innisfil at the base demand level. And the values here are showing that there are low inequality rates among income, seniors, young adulthood, employment, single parenthood, and low education, actually. And high inequality rate among population density, meaning that there are higher trip productions in areas with the lowest population density, which is likely a result of passengers using or returning home from work, shopping, or large parking. And then we evaluate the equity distribution in waiting time, in-vehicle travel time for on-demand transit systems at the base demand and the highest demand levels. And in general, we can see actually that there are the same equity distribution among the transit systems. Income has or is associated with the lowest inequality rate, while the population density is associated with the highest inequality rate. So what are the key takeaways that we can take from these results? For the crowdsourced on-demand transit systems, with an adequate supply and no surge pricing, the crowdsourced on-demand transits are the most cost-efficient transit system for demands below than it was 3.37 riders per square kilometer per day. And when we have a high surge pricing, like that could result in 50% increase in the operating cost, then the critical demand drops to 1.18 riders per square kilometer per day. Incentive strategies for drivers are imperative for maintaining the adequate supply of the vehicles as demand increases, and when there is a shortage of drivers, ride-sharing can reduce waiting times for riders by 50%, and this can be noticed if you go back here. So this shows the difference or the impact of ride-sharing when we have no enough supply or a shortage of supply. Then we have some general remarks. The use of private vehicles, we found it to be more environmentally sustainable than providing public transit at all demand levels below 3.37 passengers per square kilometer per day. And the electrification of the public transit system, along with optimized charging strategies, can reduce total yearly GHG emissions by approximately 98%. Thank you so much.